Welcome to this mind-bending journey into one of the strangest and most fascinating experiments in all of physics, the double-slit experiment. Today, we're diving into something that has puzzled scientists, philosophers, and curious minds alike for over a century. This experiment challenges our most basic understanding of reality and takes us deep into the bizarre world of quantum mechanics, where things just don't behave the way we'd expect them to. If you've ever wondered what the fundamental nature of the universe is, this video is for you. By the end of this journey, you might find yourself questioning the very fabric of reality itself and seeing the world around you in a whole new light. Imagine you had a handful of marbles, and in front of you is a wall with two small slits cut into it. Behind that wall, there's a screen that can capture any marbles that pass through the slits. Now, if you were to throw these marbles one by one towards the wall, you'd expect them to either go through the left slit or the right slit, and leave two bands on the screen behind it. One band corresponding to each slit. This is perfectly in line with our everyday experience. Marbles are particles, and particles act predictably. If you toss a bunch of marbles, you'd end up with two clear lines on the screen, each matching the slits they pass through. This is what we would expect from any ordinary particle. Now, let's take this experiment up a notch. Instead of marbles, let's use light. Maybe a flashlight shining towards a slitted wall. Light, as we know it, can be thought of as a wave. What happens when waves pass through two slits? If you think of water waves, when they pass through two gaps, they create an interference pattern. The peaks and troughs of the waves overlap, amplifying or canceling each other out. And sure enough, when we shine light through the two slits, we don't get just two bright spots on the screen. Instead, we see a series of bright and dark bands, an interference pattern, indicating that the light waves are interacting with each other. This tells us that light behaves like a wave. But wait, it gets even weirder. Physicists later decided to run this experiment with something even smaller: electrons. Electrons are the tiny particles that make up atoms, and we usually think of them as being like those marbles, tiny, solid bits of matter. Scientists shot electrons one by one at the slitted wall. And here is where things start to get really strange. If electrons were simply particles, we'd expect them to behave like the marbles did, creating two bands on the screen. But what they found was an interference pattern, just like the light waves. Somehow, these individual electrons were behaving like waves, not particles. Now, you might think, wait a second, how can a single electron, a tiny particle, interfere with itself? To make things even more mind-boggling, the scientists slowed the experiment down, firing one electron at a time. Even then, over time, an interference pattern appeared on the screen. This suggests that each electron was somehow going through both slits at once, behaving like a wave and interfering with itself. This is where the concept of wave-particle duality comes in. Electrons, and indeed all quantum particles, can behave both as particles and as waves, depending on the situation. It's almost as if they have a split personality, and which one they choose to show depends entirely on how we set up the experiment. At this point, physicists wanted to dig deeper. They wanted to know, which slit does the electron actually go through? So, they set up detectors to observe the electrons as they pass through the slits. And here's where the quantum world gets even more mysterious. The moment they tried to observe which slit the electron went through, the interference pattern disappeared. Instead of behaving like a wave, the electrons started acting like particles again, creating two distinct bands on the screen, just like the marbles. This is called the observer effect. The mere act of trying to measure or observe the electron changes its behavior. But what does observation mean here? It's not that a person is sitting there watching the electrons. It's the interaction between the electron and the measuring device that collapses the wave-like behavior into a particle-like behavior. This phenomenon is known as wave function collapse. The idea that quantum particles exist in a kind of probability wave until they are measured, at which point they choose a definite state. It's as if the universe is keeping its options open until it's forced to make a decision. But why should the simple act of measuring something change the way it behaves? This is one of the greatest mysteries in quantum physics. It's almost as if the electron knows it's being watched. When it's not being observed, it takes on the form of a wave, existing in multiple states simultaneously. When we try to observe it, it suddenly decides, okay, I'm a particle now. It raises the question of whether the act of observation itself creates reality. Of course, this doesn't mean consciousness directly influences particles. It's more about the interaction between particles and measuring devices, but the implications are still profound. So, what does this all mean for our understanding of reality? Well, this experiment raises some fundamental questions about the nature of the universe. If particles can exist in multiple states until they are observed, what does that say about the role of the observer in shaping reality? There are different interpretations of what's happening here. One of the most well-known is the Copenhagen interpretation, which suggests that particles exist in all possible states simultaneously until they are observed, and then they collapse into one definite state. In other words, reality at the quantum level is fundamentally probabilistic until we measure it. Another interpretation is the many worlds interpretation, which suggests that every time a quantum event happens, the universe splits into multiple parallel universes, one for each possible outcome. According to this view, when the electron chooses a slit, it actually goes through both, but in different parallel universes. This means that there could be countless versions of reality existing simultaneously, branching off every time a quantum decision is made. It's a mind-boggling idea. Each choice, each measurement, leading to an entirely new branch of the universe, with a new version of you and me in each one. The double-slit experiment leaves us with more questions than answers. Why does observation change the behavior of particles? Is reality itself dependent on whether we observe it? And what does this mean for our understanding of the universe at large? Quantum mechanics doesn't give us definitive answers, at least not yet. What it does give us is a framework that describes how things behave at the smallest scales, even if it defies common sense. And that's what makes quantum mechanics so incredibly fascinating. It's a realm that forces us to question our assumptions about reality, to reconsider what we think we know, and to embrace the idea that the universe is far stranger than we can possibly imagine. This experiment also highlights the limitations of classical physics, the physics that describes our everyday world, in explaining the behavior of very small particles. At the quantum level, our classical intuition breaks down, and we are left with a reality that is far stranger than anything we experience in our day-to-day lives. It's almost as if the universe operates on two sets of rules, one for the macroscopic world we can see and touch, and one for the microscopic world of quantum particles, where probabilities, superpositions, and wave-particle duality reign supreme. So, the next time you look up at the stars, or even just glance around your room, remember that beneath the surface of everything you see lies a hidden world governed by strange, beautiful, and almost magical rules. The double-slit experiment is just one glimpse into that hidden quantum world, but it's a glimpse that has revolutionized our understanding of what reality is and how it works. It shows us that there is much more to the universe than meets the eye, and that our everyday experiences are just a tiny piece of a much larger, much stranger puzzle. And as researchers continue to explore the quantum realm, who knows what other surprises might be waiting for us? One thing is for sure. Quantum mechanics challenges us to think beyond our everyday experiences and reminds us that the universe is far more complex, mysterious, and awe-inspiring than we could have ever imagined. The more we learn, the more we realize how little we truly understand. Thanks for joining me on this journey into the quantum world. If you found this video as fascinating as I do, don't forget to like, subscribe, and let me know in the comments what other quantum mysteries you'd like to explore together. Until next time, keep questioning, stay curious, and remember, the universe is always stranger than it seems.